Great. All right, we can go ahead and get started. So my name is Will Weeder. I'm the co-chair of the Land Model Working Group, and it's my pleasure to introduce Huilin Huang, who's visiting from University of Virginia, where she's a newly minted professor in the Environmental Studies Department, a few months into her job. And before that, Huilin was working at PNNL as a postdoc and a project scientist, and before that she got her PhD in environmental studies at UCLA. Her research are in land use change, wildfire, and land-atmosphere interactions. And so I think I'm excited about your visit because Huilin was here like a month ago for the UCAR members meeting. And after coming here for a month, or after coming here, she wrote to me while she was still here. And was like, hey, I need to come back and talk to you guys some more. So that's what prompted her visit. And today she's going to talk to us about wildfire dynamics and the interactions between climate ecosystems and humans. Welcome.
Thank you, Will, for introducing me and for hosting me. It is a great honor to present my work today. Today I was speaking about the burning question, but may be familiar for most of you. So we'll be talking about the wildfire dynamic and its interaction with climate ecosystem and human. So I won't go further details about my research, but just starting that I have been starting using the fire model since my PhD from the perspective of dynamic vegetation model. Then at PNL, I extend more of my expertise in remote sensing as well as the hybrid modeling, incorporating more energy infrastructure safety related to fire. And finally, I'm now exploring more topic in the fire in the wildland-urban interface, and a lot of my research will be presenting today. And just for some brief overview, as most of you have already aware of, at the beginning of this year, Los Angeles has experienced tremendous fire. So there is a Palisade fire on the west and Eaton fire on the east. Both of them are very close to UCLA. And a lot of my friends were seriously impacted because the fire was very intense and also spread very fast. And before the fire, LA has gone through 8 months without any rainfall, therefore bringing very high dry fields. And then when the dry and hot Santa Ana wind came, so the fire spread very fast in just 1 day and bringing a lot of damage and losses to the local people. And the extreme wildfire in LA is not isolated event. And in fact, there is tremendous increase in almost everywhere in the Western US. As you can see from this figure. So there's tremendous increase in both burn area and fire activity, fire occurrence. And this is in response of the drying and warming climate, fuel availability, as well as human activities. This is also including Colorado, as most of you have already experienced. Surprisingly, when we look at the global fire over the past 2 decades, we see that in observation, there is a decreasing trend. Although the trend is not very strong, it is significant in the past 20 years. And looking at different regions, we found there is significant decrease in the Southeast Asia and also in West Africa. And meanwhile, also increase in the Western US, Australia, and as well as the Southern South America. So this raises important questions. What has caused this increase and decrease of wildfire over the world in different regions? This is the first question we aim to explore. And beyond the fire drivers, another key question is their impact. Fire has caused thousands of people losing their lives. And also the hazardous air quality has brought a lot of respiratory issues. Meanwhile, fire has caused tremendous forest loss, which destabilize the hill slope. And when there's extreme precipitation, there are a lot of landslide and debris flows. And this figure summarizes the fire impact on the ecosystem, on the Earth system, which can be seen from multiple parts. First, on the lowest part, fire has an impact on different ecosystems through disturbing the coexistence between different species and tree and grass, different plant function types. And because of the divergent impact, it will influence the ecosystem composition. And the changes of surface properties will influence the water and energy fluxes through ET, albedo, and vegetation composition. This will influence the near surface atmosphere as well as the boundary layer processes. And meanwhile, the aerosol and cloud process is also disturbed. And when the aerosol is deposited on the ice and snow cover, they will accelerate the snow melt and bringing further impact. Finally, the change of surface layer will also be transported to the upper layer, influence the climate through precipitation, temperature, and wind speed. This can happen on the global scale from the full coupling between fire ecosystem and climate. So seeing the historical fire dynamic and their impact, here comes our key questions. So in this, we are aiming to better predict and prevent the fire, and also trying to mitigate their impact. The first question I will be talking about is how do climate and human factors driving the global fire regimes? The second question is how do human activity influencing specifically the US fire? Because with more active human activity, US fire has shown tremendous differences compared to the global fire regimes. And third, we will be looking at how do fire reshape the terrestrial ecosystem. And I will be looking at both forest ecosystem in the US and savanna in the tropical Africa. To answer the first question, I will be looking at key drivers such as fire weather, fuel, and human activities, and how this will influence fire regime. And so to achieve a process level understanding of fire during my PhD, I have developed a fire model, and I have incorporated the CLM Lee fire model into the SSIB tree dynamic vegetation model. And I'm aware that many of you are very familiar with, so I will be brief. I will skip all the technical details, but only mention that the burn area in the Lee fire model is transported to the tree vegetation model every 10 days, and this will influence the vegetation fraction as well as surface properties, which will feed back to the fire model in the next time step. And as far as we know, we apply a very frequent coupling between the fire model and the dynamic vegetation model, which means that we allows more faster response of fuel load change after fire. And evaluation against the satellite observations, we have captured the major fire regions in the Africa, South Australia, and Southern South America. And according to the latest fire model intercomparison project, our model performed the best out of the 7 fire coupled dynamic vegetation models, because it accurately captures the global burn area as well as the long-term variations. So using the fire models, we are able to separate the impact of climate change and socio-economic impact on fire. For example, by comparing the transient climate with the climate fixed at 1901, we can see that so climate change has increased burn area by about 16% on average. So this will having due to a drier and warmer climate. And meanwhile, by comparing the simulation with transient socioeconomic conditions and with the socioeconomic condition fixed at pre-industrial, we have seen that the human forcings have significantly decreased the burn area by 19.1. So you could imagine that in combination, so comparing both the socioeconomic factors and climate change, this will bring a slightly decrease of burned area by about 5%, although there is a significant heterogeneity in different regions. And the socioeconomic impact is reflected by the agricultural expansion as well as the human suppression related with population density and GDP. So in summary, by investigating different drivers of fire on the global region, we show that the warming and drying trend globally has increased the burn area, while the human activity tend to suppress fire. And well, we have seen that over the global region, so most of the fire models or fire coupled DGVM have well represent the burn area spatial distribution. We found that over the US, like the model performance, all models fail to capture the burn area. On top, I'm showing the latest observation from G55 and right showing different DGVMs. And this is because there is a more complex interaction between the fire, human, as well as ecosystem interactions. And because we have an incomplete understanding of this, we are not able to adapt math equations that can definitely describe such kind of relationship. And therefore, current process-based model adopt an oversimplified way to describe human factor, which is especially influence the US fire predictions. So recognizing the limitation of process-based model, our recent work has introduced a machine learning fire model, which adopts the same input variable as CLM-Li. And the machine learning fire model called the machine learning for fire has also predicted the burned area and transported to the E3SM land model. The E3S on the monthly frequency, and the E3SM land model will update the surface properties, the fuel type, fuel load, and social fuel type and fuel load into the machine learning model to predict the fire occurrence in the next month. And clearly, we can see that compared with all the process-based model, ELM machine learning for fire has greatly improved the US fire prediction. And this implies that the data itself contains some key information, which is not adequately incorporated in the physical equations, but is already in the data, can be further improved in the future. And in addition to the spatial distribution, we are also looking at how the machine learning fire model and the process-based model in different ecoregions, and to have more mechanism level understanding. For example, here I'm showing the fire seasonality in the Western mountains, meaning the green regions here. And clearly you can see the red color indicate observations from G55. The blue color is the ELM machine learning model, while all the thinner lines represent different physical model. And in the Western mountains, the fire season spread from July to November, and which is mainly driven by the hotter and drier weather. And as you can see, almost all the process-based model and ELM machine learning for fire has captured the seasonalities with normalizations. So this means that for the climate-driven fire, so both models are doing pretty good job. This is in contrast with another fire region, such as the fire in the Great Plains, in the yellow region over here. As you can see here, there are two dominant fire season, peak season. One is the early spring. The other is end of November. So a lot of past fire have happened. So these fires are used to clear the crop residue, kill pests, and also recycle the nutrients. And we found that the machine learning fire model, the blue line, has generally represented two peak seasons. This is they have studied from the data and can reproduce the general two peak season. In contrast, all the process-based model has simulated a single summer fire season, which is generated from their input this year, hot summer, and predict a lot of fire. And this means that the process model generally driven by the fire weather and ignore the human activities, which means maybe the key reason why they do not simulate the fire seasonality correctly. And in addition to the agricultural fires, the power line ignition is also received a lot of attention in the recent years. So here I'm just showing some key reasons causing the power line ignition through either direct contact, arcing, conductor sag, as well as the equipment failure. And there are also environmental factors that inducing such kind of power line ignition. For example, during hot weather, can increase the conductor sag, and also strong wind increase the probability of direct contact and equipment fault. And also the vegetation dynamic, for example, more fuels closing to the power line and increase the flammability will increase the ignition possibility. And especially we have found that, so the power line ignition, as shown here, although they only contribute to 3% of total fire count, they have been contributing to more than 10% of the total burned area. And this indicates that this power line ignited fire has bigger fire size compared to other type of fire. And maybe because they occur in general remote region and are difficult to spot as well as the suppressed. And these fires are highly influence the infrastructure safety and cause outage equipment damage. And at PNL, my second project has been leading this power line ignition scheme using the machine learning model. And here we are using the fire occurrence from the US Forest Service FPA FOD dataset. This data specifically identifies different sources of fire. We also use the transmission line from the high field. As you can see, there are a lot of fire occurred, but not in the western US except for the California. The major region including Texas, Florida, Virginia, as well as South Carolina and North Carolina. So this also heightened the fire probability in regions that do not receive a lot of attention in previous studies. And this high field data, including a lot of information related to the voltage, owner, connecting substation, line lines, and line type. And in our study, we use the overhead line, and we also rasterize all the other information, especially the voltage. We select the maximum voltage in a pixel, as well as calculating the sum of line lengths in a pixel. And also, we are trying to do some preliminary analysis to see how different factors influence the power line ignition. And on this figure, I'm showing some preliminary results to see the power line intensity as well as grass fire probability, as well as forest fire probability. We see that in general, more power line and there will be more fires. And for grass fire, this relationship is more apparent. And grass fire is monotonically increased with power line ignition. But for forest fire, it's increased from the low density to mid density, while from mid intensity to high intensity, the forest fire almost fluctuate. And meanwhile, we found that fire count is also influenced by the voltage range. The higher voltage, there will be more power line ignition. So based on the machine learning for fire we previously developed, we further incorporate the transmission line information with topography, trying to predict a higher resolution fire prediction. And similar to previous study, all this predictive fire will be incorporated into the ELM BGC, the vegetation model, and which will influence the fire conditions in the next time step. The only difference we have is we are adding the power line intensity as well as the voltage in this, and we are predicting only the power line ignition. And this is still an ongoing work, but we are able to getting some very exciting results. And by comparing the latest power line ignition from the observations as well as the fire models, we see that the model is able to capture fire in a lot of major fire regions, such as Texas, California, Florida, and South Carolina, North Carolina. In the next times, in the future, we are trying to apply this model to attribute the changes of power line ignited fire due to different environmental factors as well as the human implementation. In summary, by investigating different drivers of fire, we have seen that machine learning hybrid model provides a useful tool to simulate US fire with incomplete physical understanding. And also we find that machine learning model is also able to reflect how the line intensity and voltage impact into the power line ignition. And with an understanding of the fire dynamics over the past decade, so now we ask, how do wildfire reshape the terrestrial ecosystem? And I will be mostly using both remote sensing data and fire model, trying to see how the burn area and intensity influence US forest mortality and savanna tree grass coexistence. First, we are trying to understand the mechanism that's causing this canopy loss or mortality. After fire, we found there's an immediate forest loss happening in the fire year. This immediate loss is mainly caused by the flame consumptions as well as thermal mortality. When the fire temperature higher than 60 degrees, so there is immediate tree deaths and causing during the fire. And both fuel consumption and thermal mortality is related to the fire intensity, and which is very popular. So fire intensity describes the fire release, energy released by a fire. As you can see, I showed different photos of fire of low intensity, medium intensity, and high intensity. Apparently, they will cause different impact. And the fire intensity can be further divided into the conductant and convective heat as well as radiation. And the radiative part, the fire radiative power, can be directly measured from a satellite, such as spheres or ghosts. Therefore, they will provide a spatially and temporally completed fire fire behavior from satellite, which will be giving us more information about the fire characteristic over the large scale. And beyond the immediate loss, we are also looking at the delayed canopy loss or delayed mortality. So the delayed canopy loss occurs when there's no a few years after fire. Although there's no fire happening anymore, the trees continue to grow even though there's no further fires. This delayed loss is mainly driven by the heat injury. So the heat injury of the xylem in the tree's crowns, stem, and roots, and making it harder to transport nutrients and water from the root to the top, and therefore it will eventually cause the tree to die in a few years. In most fire models, such as the CLM-BGC, the delayed loss is not considered, which means that a kind of very important mechanism is probably missing in the current DGVMs. And in a recent study, I quantified the fire impact of immediate and delayed loss in over the whole US forest. And this figure just summarizes some steps of my methodology. For example, we filter out all the fire hotspots near the fire line. We emphasize it is only across the fire line. And also for this fire hotspot, we extract the fire-related power, vegetation conditions, as well as the nearest climate conditions, and seeing their relationship or how the different contributors contribute to the tree canopy loss. And the tree canopy loss fraction is defined as the canopy loss area divided by the forest burned area, normalized only to the forest burned fraction. And we found that in our study, we found that immediate canopy loss is larger in Southern California, Northern Rockies, and Southern Rockies, including Colorado. So for this region, the immediate loss is larger contributor. And the fire, we have done different significant tests for different factors, and it reveals that FRP emerges as the dominant factors. As you can see, before around 100 watts per square meter, there's an exponential increase of the canopy loss fraction with FRP, and which gradually flat after this range. And this the FRP represents the fire radiative energy, and which both directly relate to the fuel consumption as well as the thermal mortality. Therefore, there's no doubt that this is the most important factors. And in addition to the FRP, we also see that the post-fire forest structure represented by the canopy cover and canopy height as well as NEVI is also an important contributing factor. Here I'm only showing the tree canopy cover. As you see, they exist a hump-shape relation, meaning that immediate loss peak at moderate pre-fire cover. And it will decline on both sides. And the relationship between the tree canopy cover and tree canopy loss is parallel to those of tree canopy cover and FRP, which means that the tree canopy cover influences the canopy loss through modulating the fire RP, through changing the fire behavior. Let's try to understand the mechanism behind it. So there are two mechanisms influencing this relationship. First, at the left part of the figure, so for the sparse canopy or open space, we can see that there's a the forest has kind of limited fuel continuity. Therefore, with more canopy cover, there will be increased fuel continuity, which facilitates the fire spread and becoming more intense, and also facilitates the fire to become from surface fire to become crown fire. And at the right part of the figure, we can see it represents more closed canopy, and meaning that as the closed canopy cover increases, with more canopy cover, there will be higher fuel moisture as well as more stable boundary layer. And no wonder that in this part, there will be suppressed fire activity in the closed forest. So with a brief understanding of immediate canopy loss, now we look at delayed canopy loss. And this is used by the same canopy loss fraction, but looking at the forest loss after fire year. And we have clearly seen that this delayed loss is larger in Northern California, Pacific Northwest coastal forest, as well as the Northern Rockies. So unlike the immediate canopy loss, we found that delayed loss only shows weakly relationship with FRP. So this further representing that they are influenced by different mechanisms. And although we see that there is a slightly Huang-shaped relationship, meaning that FRP, when FRP at moderate level, it will bring more delayed canopy loss. And this is also expected because with the higher FRP, we will see more immediate loss. So like at an intermediate level, this will bring more delayed loss. And for the delayed canopy loss, we found it increased significantly with the canopy cover, and it will stabilize at a higher value. So the canopy loss fraction increased from nearly 0 to around 30 to 20 to 30% at a higher canopy, at a, oh, sorry, I labeled the wrong name. It is a pre-fire canopy cover. And this relationship likely reflects the pre-fire competition. When there's denser forest with denser and older forest, it generally experiences greater competition for soil moisture, nutrients, and light after fire occurs. And with higher competition, it will be likely a decreased likelihood of recovery and more mortality. And compared with immediate canopy loss, we also found that the delayed loss is more strongly influenced by climate factors. This is reviewed by both climatology factor as well as climate variations. For example, we see that the canopy loss decreased significantly with climatology temperature and vapor pressure deficit. This is beyond expectation by many people. However, if we look further, for example, we can see that we will see that moist and cooler forests, as shown in the blue shade here, they generally will have higher forest loss. This is because they have infrequent wildfire, and in the long-term fire ecosystem climate interaction, they kind of lack the fire-resistant trees. They don't have the thicker bark or deeper roots, and when the fire really occurs, they are easy to dead after fire. And in addition to the climatology patterns, temperature and VPD anomaly are also major factors influencing the canopy loss. We see that as temperature increase from cool anomaly to hot anomaly, VPD from wet anomaly to dry anomaly, the canopy loss increased by 2 to 3 times. This is likely reflect the influence from compounded stresses. For example, when fire occurs in the year with heat wave and droughts, the pre-fire injury will also will making the trees weaker to other disturbances. So this reveals how the compounded stresses significantly influence the vegetation resilience. So in summary, in this, our recent work has reviewed 2 different pathways for immediate and delayed canopy loss. And on the left, I'm showing the immediate canopy loss, in which the fire directly consumes a lot of plant tissues and also causing the thermal mortality. And in this immediate mortality, and we will see that the fire regime will play a dominant role controlling the magnitude of immediate loss. And meanwhile, we found that the vegetation status, such as the canopy cover or height, will influence the field structure and combustibility, which further contribute to the fire regime changes and finally contribute to the immediate loss. And meanwhile, we are looking at the delayed canopy loss. And in contrast, we found that this type of delayed canopy loss centering more on the delayed loss after the fire year. And for this type of canopy loss, the pre-fire competition is an important or dominant factor of fire-induced delayed loss, which is really related to the vegetation canopy, NDVI, and vegetation height, and reflecting the pre-fire competition after which will be important for the post-fire recovery or competition of soil moisture and nutrients. And meanwhile, we found that the pre-fire injury of climate stresses, such as droughts and heat wave, weakens trees, which also reducing their resistance to the subsequent fire years. And in the previous slide, we see that in the U.S., wildfire has driven widespread forest loss and raising concerns for the local forest. However, we found that in other regions, fire plays an important role in maintaining the local ecosystem structure and function. Here we examine the fire impact in the southern hemisphere Africa. In this region, fire burn area fraction is higher than 50%. And this indicates that the fire recurring period is every 1 to 2 years. And we can see in this region, the fire season spans between July to October, and which peaks in August. And this figure showing the temporal evolution of vegetation fraction change during the fire season and the following rainy season. And the red line again is showing the burned area. And the two bars generally show accumulated grass cover reduction and tree cover reduction. Clearly, we find that the grass cover reduction accumulate during the fire season and peak at the end of fire season. However, during the rainy season, it's rapidly recover and almost disappear the effect and at the end of rainy season. And in contrast, we see the darker green bar, which is tree cover change. Although this is very small, less than 1%, it is non-recoverable in one rainy season. And this indicates that there will be divergent impact of fire on vegetation, on trees and grass. And given that fire, the divergent impact, we are asking what happens if fire disappear entirely? And by comparing the vegetation composition in the current real world with fire and an idealized experiment for a world without fire, we can see that fire has greatly influenced or reduced the tree canopy cover over the tropical savanna, with the increase of grass cover increases. And this indicates that without fire, the tropical savanna would gradually transition into the woodland, with trees encroaching into the savanna. So as you know, savanna hosts a wide variety of wildlife such as zebras and grass. These grazing animals heavily relying on the local ecosystem to feed their nutrients. So if the savanna become forest, these animals will undergoing a lot of losses. And the result that savanna become forest may seem pretty surprising to some of you, and you may wonder if this is true. And scientists in Africa savanna, they did a long-term experiment for 50 years. They select a protected zone in the national forest and protected it for half a century. And clearly, we can see that there's a lot of trees actually growing in this protected zone, further proving that fire is a determinant for the structure and functioning of savanna. So in this last section, we examine the disturbances of fire on the different terrestrial ecosystem. And the take-home message we have is that, like, first, the immediate canopy loss will increase with FRP and also peak at moderate pre-fire cover, which is also representing the boundary of the forest. And second, we also see that the delayed loss in moist and cooler forest is larger on the moister and cooler forest and elevated in a drier and warmer year. And last, we see savanna can become forest in a world without fire. And in summary, my previous work has laid the foundation for understanding the fire ecosystem and climate interaction in a changing world. And in the future, I plan to further advance their interaction while also incorporating the human impact through the following three aspects. I won't go into further details, but will welcome to any discussions in this part. And finally, I'd like to conclude with this page. I want to acknowledge all the support I have from UCLA and PNL, and also as far as my collaborator from university and NCAR. And thank you for the attention. I'm happy to take any questions.
Are we able to use the mics for questions? Yep. Cool. Yeah, go ahead, Katie.
Thanks for your talk. I'm curious to hear more about the ML fire model. I'm wondering, how was it trained? Like, what data sets were used to train it? And it sounds like it's predicting burned area, but what is it using as input to the machine learning model?
Yes, that's a great question. Actually, we have a lot of design in the machine learning model, which I don't spend a lot of time to talk. And the machine learning model is pre-trained, meaning that we use the offline, First, we train the offline model using the climate input as well as some variable from a ELMBGC into the model. And we also trained it using a strategy with left one out, meaning we 20 years of burned area from GFED, we use 18 years for training and 2 years for testing. And based on this, we have built 20 models or 19 models and using an ensemble of all these 19 models to do the prediction. So this is our training and testing strategy. And of course, this is like the model is pre-trained and decoupled when we train the model. And that time we have reached a performance of 0.9 or even 0.95, very high correlation with observations. But when we really coupled to the dynamic vegetation model, the feedback to the burn area, as you can see, will lower the performance to around 0.7. So because of the feedback of the vegetation fuel load and fuel moisture changes, and we have a kind of deteriorated performance, but still better than all, like most of process-based models. Sam?
And as far as inputs, you said it uses the same inputs as the lead fire model, right?
Yes. Yeah, from that one, we realized probably like the data itself, the data we use in the input already have some human activity information, but this is like not well parameterized or described in the equations in the current CLML. Dave?
Well, yeah, the same kind of question about the training is there's, a lot of that's agricultural regions, right? Or pastureland, which is agricultural. So Lee does have a crop fire inclusion, but it's just, why is it not all the crop areas and just showing up in particular parts of the crop areas? What's the driver? How can you explain that?
Sorry, maybe I'm not understanding your question, but our ERM VGC does not have the crop fire, so the default one doesn't have the crop fire.
So then, where's, I'm still having a hard time, if you go back to the previous plot, the map. A lot of the stuff across the Midwest, and then, there's the stuff along the Mississippi, that's it must be agricultural related activities. So what is the driver?
Yes, so we don't specifically use a driver, but we use the crop fraction into the model. We have the input of crop fraction, and the model may have learned the specific seasonality of fire occurring in the crop area compared with Western fire.
You say crop fraction, is that broken down into the different kinds of crops, or is it just one overall, how much cropland is there?
It's how much crop it is. Let me see if I include. No, I don't include additional maps. So we have tested different. Factors contributing to the fire prediction in the machine learning model, and the top three are the moisture, temperature, VPD, and precipitation, as well as the crop fraction. The crop fraction in a pixel. So I think this do distinguish the crop fire compared to the natural fires.
Still, sorry to bang on this one horse, but it's still confusing to me. Like if there's a crop fraction in the training, I mean, it's not showing up everywhere there's crops, right? So it's very specific regions where there's crops. Like why is the Mississippi, actually in the real world or in the model, showing up as a peak fire area, right?
So I mean, that's heavily rice, right? And so it's possible that the machine learning is picking up on the climatological factors that make it good for rice and associating that with the cropland there.
Thank you, Sam.
While we're on the machine learning model, it sounds like you're using an ensemble of models. Can you talk a little bit about that choice to kind of get a stochastic output from the model?
What do you mean by the ensemble and the stochastic?
You're using an ensemble of ML models.
Yeah.
You run them all at each time step, and then you take the full distribution, or you sample from one of those. And can you talk about why that decision was made? Did you just take the mean of all of those?
We take the mean of those. Like we were just using it as an ensemble climate model strategy parallel to that one, trying to include more predictions, given that some of the fire model may not be good, depending on, because fire also have big interannual variability. So in this way, we are trying to more the average or kind of decrease the impact of interannual variability on the specific training and testing data. Yeah.
Can I ask a question about the power-induced fires?
Oh yeah, go ahead.
One is just like a question about the data itself. Like, it seemed like there was no fires in Georgia. And like, you can almost see state boundaries on the observational data that you're trying to train to, and I'm wondering if that's real, or, sorry.
Power line fire.
Yeah, in the human part.
Oh, yes. So I think you got a good question. So the power line ignited fire is very strongly influenced by the state policy. For example, we see the Texas and Oklahoma as well as Florida together with Georgia. So because those states have very different practice on the forest management or the power line management, I know that Texas do not do the kind of branches cut before the fire season, while the other state having a lot of policy maintenance before the fire season. So this practice has greatly influenced how they behave differently. As you can imagine, these two states are very close to each other and should have similar climate background, but because of different human activities, and they do not perform as similarly. And for this type of we don't actually have a specific information in their practice, but we are trying to add in the state information into the machine learning model, trying to imply that different states may have fire is influenced by the state policy.
So I guess that was my first question. So the observations are real.
Yeah, this is observation.
Georgia has.
It's not state level observation.
No, yeah.
This is a global. Yeah.
That's what I
Yeah.
think that alone I think is astounding that you can see this from space. Yeah. And so then the machine learning model, that was my next question, is like, if the observations are real, then what do you put into the machine learning model to capture those? Like, are you training like on a pixel level, or? I guess I was surprised to see that the machine learning got the observations right, and I'm just curious what it was that went into the machine learning to capture that.
Yeah, that is also a great question. We spend a lot of time training the power line igniting model. And so different from, not different, it is more difficult because there are even limited power line ignition. I think we are currently only evaluating on the climatology scale, and which bring us more data point for training. And we are using by leveraging both GFED as well as FRP. So we have two data sets. This data is on the point base, which represents the fire ignition or fire starting point, but this doesn't give us a spatial distribution of the fire shape. And we added this data set together with the GFED, which give us information on the GFED pixels, which may be with the same months of power line ignited fire. So we attribute the months with FRP data and also exist with the GFED as a power line ignited fire. So using the power line ignited fire burned area and the fire counts, and we are trying to train this machine learning model and to getting a fire probability. And I forgot to explain the fire probability does not equivalent to the fire count as you see on the left, but specifically, they are kind of generally representing the higher probability of fire. And this is a kind of intermediate variable in the fire model. And finally, we are trying to reproduce the burn area as you show in the GFED. Jim?
Yeah, hi. Can I ask maybe it's a silly question? So for the machine learning model and then the first part about climate, so the model is predicting the burn area, but do we know when or under what condition would this fire would occur?
So you are asking the fire occurrence or?
What are the favorable climate condition or weather condition would fire occur?
Yeah, I think there is like a lot of mechanism level of like maybe the drier condition or hotter climate with strong wind, the fire has a higher probability to occur. The things like the model we are built is specifically we are trying to predict the burned area in the Earth system model or land model, which can be further used to predict the fire impact on the carbon cycle, probably on the climate scale. It is I may need to say that it is not for the single fire event or to predict event scale fire happening, but on a more climatology. If we looking for 20 years fire probability or fire probability on like 10 kilometer to 10 kilometer spatial scales, we are looking for such kind of patterns. Yeah, and also because there are two very important components. One is the fire weather, the other would be the ignition. And ignition is something like even more stochastic. And for example, as the first, I have like showing the example of Los Angeles fire. And because there are 8 months without any precipitation and also strong wind, so this city is just like a tinderbox. Wherever there's a fire spark, and it is very easy to get ignited. So I think if sooner or later there will be a fire happening. So in that case, I think this is like the fire ignition is more difficult to predict compared to a climatology fire burn area patterns. Thank you. Adrian?
Yeah, I mean, I liked all your talk. I really love the part about the ecosystem and like the fire mortality. I feel like that's the part that we could really benefit from using in FATES. Like, so whatever, updates, because I mean, it really follows along with like the model that we already have, like the theory that we already have in the model, but in the Spitfire model, but I think like maybe the exact parameters or, so you're doing this in the US, but it would be amazing to be able to apply this, what you're learning here, like globally. And if that means we need like different parameters for different PFTs or like other conditions. So I don't know. Yeah, I don't know if you've thought about that.
Yeah, thanks for asking. Yeah, because some part like we really get some very exciting result and like just prepare to submit. And I'm feeling that this is very relevant to the phase for the phase Spitfire for the development, because we are trying to quantify. Previously, there are a lot of mechanism level understanding of the different factor influencing fire, but on the regional scale, especially even on the corners in the US forests, such kind of large scale quantification or attribution to different factors sometimes lacking. So we are trying to getting some more generalized or statistically significant relationship and trying to see how different factors are contributing to the post-fire canopy loss, like immediate loss and delayed loss. I feel there's a lot of potential in kind of reassess or to see the phase mortality scheme and like doing some comparison with the observation. I feel there is large potential to further like develop in this part.
Yeah, I totally agree. Yeah, so please stay in touch. Yeah.
Any more questions? And I'm not normally in charge of the seminar, so I don't know when the next speaker is, but I'm assuming it's next week on Thursday.